So we're just going to review a little bit about what we did yesterday to begin, just for sort of 5 minutes, and then we'll talk a little bit about what we're going to do today, or vice versa. So yesterday we covered, so go through some of our learning objectives, things we wanted to cover. We've done sort of have a broad understanding of the advantages of GPUs and CPUs. We discussed some of the technologies involved, and we looked at some of the design decisions made between the two hardware architectures and what that means potentially for performance and what that makes available to you. We understand how data movement is done in a simplistic way. There's multiple ways of doing this, and we'll come on this today a little bit about moving data. But we have a way of moving data between device and host now, and we've written some example kernels. We've also started to discuss things like occupancy in order to drive performance. We've discussed it in terms of how to make sure a single kernel provides good occupancy. What the last part of today, beginning tomorrow, we'll discuss is methods to make sure that sort of kernels working together can provide good occupancy a little bit. So we've done half that kind of story. So what will come on today is talk about, we've done performance considerations, managed memory, shared memory, constant memory, and then streams to finish off. Then tomorrow we'll cover graphs and a bit of a device management before doing a larger example to finish off the course. So first up this morning, we've got 45 minutes to kind of just review a bit of what was covered yesterday. And then there's a little, so I'm going to go through the example at the end of yesterday in a little bit of detail, because this is kind of the, if there's one section that you really want to have understood, it's this ordering of how data is transferred to device and then run. So I kind of want to be a little bit laborious in discussing that. That will take probably 15 minutes for me to go through that. And then I'm going to hand it back over to you guys to do a little example about using some of your outputs from RockProf in order to look at some profiles. So there's a couple of profiling tools which you can get access to freely, which I'm going to give you guys up until the break to have a play with. Those of you who've got outputs from yesterday's session can use them to do the visualization. They'll be useful for the rest of the time to when we're comparing, especially managed memory and other bits later, to see what calls are actually happening and what order. So hopefully that will provide a bit of a better a way to see visually what's happening with the timings, and it will also help to illustrate some of the limitations which getting memory management in the right location starts to cause, because you'll start to see how big of an impact data movement is relative to the whole kernel operation, as well as the physical launching of a kernel to start running is quite a high overhead. And that's where streams and graphs can come in to try and reduce some of those costs. They'll be very interesting tools them today. So, is there any, first of all, are there any questions from yesterday's material anyone wants to jump in with now before I start going through this example? Good, silence, that's great. Okay, please do ask questions. Once again, we have the Etherpad that I will now link up so that people have access to it. Additional questions out of the course. So if those who don't want to put stuff in the chat, I think they're being missed out. I'll try and refer to this regularly so that I can see if there's any extra questions that appear. There. Okay. So let's just get away from that for now. get this environment up. So just going to briefly skim through this again. So the point here I really want to kind of hammer home is this bit about ordering and making sure that we have contiguous threads accessing contiguous data. So this is the key difference between a CPU and a GPU, and it will give you a performance improvement. You can get it to give reasonable performance improvement versus doing things as serially as you've probably seen yesterday. But this is the kind of key design difference. So in this example, we started out with a very simple kernel implementation, which just serializes everything going through a single thread and gets terrible performance. And then we need to slowly remove the loops to give improved performance and see how that does. So starting with that. So let's get I'm set up correctly. So I'm in the directory that has this example. Pretty sure I haven't edited this in any way. No, I've got blank kernel stub at the top. And I've got an area where I need to be running this here, and I've got some setup information for running things in multiple dimensions. Okay, so I need to edit this in order to get it to work properly. So our first job is to do kind of the simple naive thing and make everything serialize. So for that, I'm just literally copying what was recommended in the example. I'm not going to go through it, I'll just put it in here now. Show it you and make sure it's clear what that's doing. So what this is saying is get my, oh, I need to actually provide a thread, that'd be good. Means I'm going to start my kernel. I'm going to launch it with some parameters. And I'm going to say, for every single thread, I give some extent of this array that I'm going to operate on. Remember, we're doing a very simple operation. We're just multiplying two vectors, x and y, together to fill in a matrix A. And we've decided to describe A, the matrix is just a array for simplicity. And we are updating this, and then we're going to pass it back to the host and check it against the host doing the same calculation. In this example, we've serialized the threads, and we said only thread 1 is going to do, the thread 0 is going to do any operation whatsoever, which is going to be incredibly slow because you're using a single GPU thread or in a single CUDA, in a single compute unit, a single streaming processor, and that's going to run at a slower clock speed than a CPU, and it's going to get none of the benefits of GPU performance. This should be absolutely slower than the CPU. It's not doing anything special. Okay. However, if we come on to do the first bit of this, we then want to say, okay, I've got this iteration over I want to remove that loop initially and see how the performance does then. So check I've got my right answer here. So this is going over X. So my TID should be, I'm removing the I loop first. So my TI, so my index, my thread index, TID is going to run over some limit up to less than n. Yeah, m row. Then I'm going to put j to n column. And then this is just to replace I here. So actually, I'm just going to make everything a bit simpler. I'm just going to turn this to I. Okay, and that's going to run over fine. And then I need to check that my launch parameters make sense for this example. So down here, so X is going to run over to the extent that I want it to. So that's my in each. This is X block saying the number of blocks of threads I want to do work on. So I need to check that I can divide this into even number of blocks, and that if I have a non-complete number of blocks available to me, I always have one more than that. We're not doing anything in the second dimension, so n block y is just 1 for now. And then I need to provide this to my blocks launch parameter, and this gets run. And I get some performance out of that. I don't have that performance here. I have it over here though. So give you the sort of level of where we're working at. I then need to compile and run this. So just to make sure this is everyone's heads again, we need to set up our environment with modules. I need to load my MD module. I need to load my Rocker module. So I can compile the GPU. I need to set my compute capability for my GPU, and I've got something equivalent for the CPU settings in the environment variable to make sure everything optimal. I then can compile with hipcc. That's really annoying, it is. Okay, compile with hipcc, telling it that it's going to compile for a hip target. I realize there's more zoomed in as I did yesterday. It's going to compile for a hip target using this -x flag. It's using standard C++11. It's got some environment parameters about where to find the ROCm. It's got some information about the platform it's targeting, and then we're going to compile. And I've obviously made a mistake because I haven't. Okay. So I can look at my submit script. So in this case, I'm going to, so I've got to return annoyingly. So in my submit script, still very simple. I am setting up my IDs, the name of the job, time, and the petition I'm using. I'm using the GPU petition, and the quality of service I'm using the shared again. I'm only running one task for those who use MPI, and I'm only asking for one CPU task because I don't need any more than that for this example. In this case, I'm using rockprof again, and then the system trace out the end. And I can run this, submit this to run the code. It is. What I wanted to show you at the same time was some nice little Blue Peter example values from before. So let me just see here. So here I have the completely unthreaded version. I'm not using, sorry, this is using thread 0 only, no parallelization, everything's just going very serially, incredibly slow. And then if I remember right, I think it's this example should give me something equivalent to this, much improved speed up in 2 dimensions. It's using a single dimension to divide up a number of blocks. So is this complete? Yes. It's cat slurm to make sure I've actually done this correctly. getting very confusing for everyone. So I've got the correct answers. That's what I expect, because I've tested this on the host. And I want to look at the results, top stats, what's this thing? Okay, and I guess something's a bit slower, but it's still significantly faster than I was seeing on the previous sample. So where I've not added anything at all. So that's the one-dimensional example. If we move to multi-dimensional, so I will now want to do this 2D. I'm going to do a kind of naive, obvious thing here, is I'm going to extend this so that I have int j equals block idx dot y times block dim dot y times thread index dot y. And now I need to also do a limit here so that if I run indices that I have the correct thing. Right, if I have a block size that's larger than my total array, the threads that are above that array length aren't going to be displayed in data, they're going to display with junk, so they're just going to be told to do nothing and wait. It's a slight inefficiency, but if it saves you having to precisely tune every single block to the nth degree that you don't need to do, so that's a benefit. Okay, check if anything else wrong. So then the natural thing is we need to look at the launch parameter requirements to make sure that they're correct now with this example. So we go down the page on this section. So now I've got more than, I'm using the 2D block size, which I think 16, not 256. This is fine, I've got both these. I need to provide threads per block for both dimensions. This is 2D, this is block. This is fine. Then I need something that looks like this. Dead and col. Okay, so that's now going to do divide this up into 2 dimensions. And execute this example. Okay, I'm going to go through this just to be pedantic, but file script. And then just submit. Right. Hopefully this takes a couple of seconds. Yeah. So let's just check that it's run correctly, not have any mistakes. Yeah, we've got the correct number of results. Roll log stats.csv is being overwritten, and this is much smaller now. Okay, so you see you've already gained a performance improvement just by going to 2 dimensions here, because you've got more blocks to distribute them. More blocks can be divvied up to different compute units, and they give more parallels being exposed. There's one last thing we want to do, and that's where we want to think whether we've got contiguous memory access in our kernel. And this is kind of the last little bit, and the bit that we really want to hammer home here is that to get this correct, we need to make sure that contiguous threads are accessing contiguous memory. And to do this, we need to make a slight change. So at the moment, is the way that the blocks are organized in multiple dimensions, that X always runs first. So X is the thing that's going to run over contiguous memory. At the moment, we're doing jumps with X, right? Where Y, sort of the J element here, the Y dimension is going over contiguous threads, which means we're not actually as efficient as we could be. So to finish this kind of off, we need to do one little thing, and that's we need to change these around. And this can be as simple as just doing steps. We just change the parameters around to make sure that we're accessing memory in the right order. And then we need to make sure that we provide the right parameters into the launch to the kernel. So that just needs to change around which blocks are operating down here. So it needs to be block Y is sent for the X direction, block X. So I know this example has this, but it's a lot better sometimes if you don't think about the directionality of this can get confusing because you feel like you're going across yourself a little bit if you start labeling the physics object, this array that we're going through, as having X and Y dimensions, as well as then having the layout of the grid threads of the blocks as having X and Y dimensions, because you end up sort of having to cross over sometimes. It doesn't quite feel very natural. So just be aware that this is something that has always driven me up very easily. I need to think about it sometimes to make sure I'm doing the right thing. So this should then give an additional speed up if we compile. Again, let's just check it's what we worked properly and I haven't done anything wrong. Okay, I've got the correct number of correct answers. And I want to look at the results. Okay, and now I'm even faster. So there's a nice progression there that you can get significant speed up between results. The last little bit, I think, especially because this example is pretty simplistic, the size of the jumps we're making between rows is not huge. You're not seeing a massive improvement, but it is still a significant percentage of the result that you're seeing between the two. Okay. So Sebastian's asking, when working in Fortran with HIP, because the kernels are written in C, are the 2D arrays using Fortran or C memory layout? The arrays are using C memory layout, but the point here is that the way the threads are organized, you need to think about it in the inverse, if that makes sense. It's not that the array, the data is laid out in a different way. It's the way that you want to access it is different on the device. And that's where the confusion entered. Okay, so now to get you guys to do a little thing for sort of 15, 20 minutes. Having now completed that, what I want to show you is a couple of profiling tools which can make visualizing what's happening on the GPU a bit easier. So I've got I'll just show a couple. This is Chrome tracing. And actually, I should say something before I show this. Okay, when you run RockProf, it produces this nice JSON file. If I just look what's in there, I have a bunch of events, information about the events and timings that have come from the system as I've run this profile. And what I can do very simply is I can use the tracing tool and I can load in this JSON file. So I have what I made earlier, and then I can inspect the workflow here. Pavel, yes, I can share the last code version. It is also the beginning of the next section if you want to access it on the GitHub. And what this allows you, so this is one way to do this. This allows you to start inspecting. I'm trying to remember how to do this correctly with these different tools. So you've got movement around, but more importantly, you can do zoom if it's going to play ball with me. Oh, that's down, isn't it? So there's two tools like this. NVIDIA has something that they integrate themselves, which they provide for free if you're running on CUDA, that can start to look at that does pretty much the same thing and provides you information about the phases of kernel operation on the remote host, and allows you to start inspecting them and gets information about them. So this is quite nice. This is free. This is just an attachment to Chrome that don't think I have to download anything. So you might have to download a plugin, but I think it was pretty much there. I think this has come out of the gaming industry when people were looking at profiling there. But you can see I'm having to spend a lot of time hunting down where my actual kernel call was. So that's the last error. Here's my kernel. My kernel takes no time. It takes a few milliseconds. Whereas, or less than a few milliseconds, okay? That's the raw duration of that kernel. But everything else is taking far longer. So my mem copy is huge. My kernel launch is quite large. My mem copy back is pretty large. I'm having to do a lot just to do this tiny kernel. So this is one tool you can use. Another tool that I think is slightly nicer is this Profeto tool. And I can open the same trace file. And I get a similar result. Now, the labeling on the left-hand side is not particularly very useful. It also provides some CPU information operations as well. But what this does allow you to do, which is quite nice, is to start moving through the region. This timeline at the top. And as again, you can see the copying is humongous compared to everything else. But I can start to zoom in on particular kernels. I can get information. I can get kernels with the same name and group them. I can do a lot of things to start analyzing what's going on within my work. So what I want you to do for the next sort of 15-20 minutes is, those who've completed your runs already, I want you to either regenerate that JSON file or get it yourself. I want you to get access to some links to Profeto and Chrome trace in the chat, and I want you to try looking at and inspecting your runs to understand the flow of and the progression of your kernel execution and see what's being called. This is a small exercise. For those who are really quick and have done this already, try adding in maybe a little extra kernel call to second and see how that changes the flow of the work. Okay, so that exercise is for 20 minutes, and then we will take a short break. Okay. So I've put links into the chat to both of these. Have a look at how you can explore them, what information you can try and extract, and how this allows you to understand a bit more about what's going on in the actual execution. I think Professor actually provides you with, oh, I've changed over now. That was it. Yeah, so you can zoom with control. That's what I remember what I was doing yesterday. But you can also play with the slidey bar on the top as well. So there's a copy hosted device here. It's actually being called inside this memory copy. There's a copy hosted device happening here. Got some mem sets in this example. I'm going to go until the end. I'm going to find this kernel. I everything with the same name and things like this, and get some instructions of detail, especially things like kernel launches or hit mem copies. You can get everything with the same name. I can list all my memory copies in one go. All similar configurations, and I can start to group these together, which is quite useful to sort of look at. There's also ways to query with SQL and things like that. There's also some other stats and metrics, but they're not particularly designed like this. Okay, sorry, I'm on a Windows machine, so maybe that isn't installed. Profeto, UI Profeto is available. That's why I've tried to provide two. So they provide broadly similar functionality. This is quite common when you're inspecting what's happening on a GPU performance. Because you don't, because your execution is sometimes asynchronous, you want to be able to probe this. So just getting a feel for these tools is really useful. There's lots of others. I mean, we provide access to Linaro Forge on ARCHER2. I'm not going to try and go through a tutorial of that. That's an entirely separate training session in itself. But that does allow you to do similar profiling type techniques. Thanks, Ben. I didn't know about that conversion tool. That's really good. I personally, I need to try and find something to go the other way. I really like the Insight Systems interface. A little more experience using that. But it's good to know you can go this way as well. The nice thing about Insight Systems from NVIDIA is that it also allows you to start generating Insight Compute profiles. And Insight Compute is profiling the detail of a kernel itself, not so much the flow of a number of kernels. So what it allows you to do is then get the profiling to start on the nth kernel through the list, and provide you that setup automatically sort of generated for you, which could be make you very efficient at doing profiling. Paul, which part of the kernel is this? I hadn't noticed this, if I'm honest. I mean, it's the same data, right? It's Rob Prof's giving out this information, so I'm surprised that there's a difference. Yeah, it's not HIP launch kernel that you need to click on. That's separate. You need to click on the actual kernel at the bottom. So it's a separate layer. Yeah, you're on a different row. Exactly. So, and this is one of the limitations that Wan will come on to discuss with, and why things like streams and graphs are good, is because they start to reduce the cost of these launch overheads, which are actually humongous compared to what you're actually trying to do. And if you want to get the real benefit, that you need to find a way of doing launches a fewer number of times. So graphs allow you to try and do that. Yeah, so then you can just open these different layers up. I think the top provides you some stuff that's happening on the CPU. I'm not sure if I know all these particular operations, else I won't speak to them. Good. Is this login node, or do we feel this is we're waiting a long time for GPUs? Because my favorite thing in the world is when we do mid-training session, ARCHER2. Yeah, I'm getting hangs as well. Okay, for those who are having login node issues, try exiting and coming back in. Remember to reload all your modules and everything. Do and see if you get a different login node on try. Yeah, so login node 1 for me is slow. Okay. Juan, could you possibly contact Service Desk and see if there's any ongoing issues?
Yes, I'll have a look. Maybe this is like a sign of go for a coffee.
I doubt it's because everyone's trying to compile, because that would be pretty bad.
I mean, I guess
shouldn't be.
yeah,
the usual thing is there a high load at the moment, and I'm not sure we're causing that.
Yeah, I'll have a look.
So, I mean, my plan was to take a 10-minute break at 10 to 10. Trickier to fix. So what I suggest we do is people want to take a break now, and we'll come back and we'll give 5 minutes to keep trying this example, 10 minutes to try the example, and we come back before we move on to the next topic before lunch. And we'll come back at like 5 to 10 and see if it's improved, and that will give me a little time to go and see if there's anything wrong with our support team. But I will be around on the channel, so if there are questions that are coming in, do that. Yifeng, which tool are you using? Are you using, I both get 4 here. Yes, it's a bit odd you're only getting 3, but the main thing is that as long as you have a kernel one and you have the HIP launch bit, so the HIP calls and the kernels themselves running on the device, those are the main things I just want you to inspect, to be able to find them and have an understanding of how these tools work. That's the main outcome of this. Because this is quite a common tool setup to be able to visualize what's happening in the GPU. That suggests that you haven't actually launched anything on the device. So do you know from your, so that means there's no data in the output from prof. So is there any information? So if you go into results.stats.csv on ARCHER2, I mean, that might be difficult at the moment. Can you access, can you see that there's a result there related to this performance? And if there's not, then you may have not launched the kernel correctly. Back, that's good. I know what slideshows. Yes, my one also seems to be back now as well, which is good. Okay, so I had a moment, and we're okay. Okay, so keep having a go with this for another 10 minutes. Start the next topic at 11. I'm going to take a short break. I'm going to get a glass of water. And when we come back, we will be looking at managed memory, and we will have more opportunities to use these profiling tools throughout the day. So if you feel like you want to take a break, you haven't quite got there yet, then don't worry. There'll be more chances to look at this. Okay. So we're now going to move on to another topic. Before I do it, any final questions on the profiling or any of the occupancy and contiguous memory management we reviewed this morning? So what we're going to look at now is called managed memory. And while this may seem like a slightly easier way to do what we've just done, it's not very performant necessarily. Okay, screen. So here provides a number of different ways to establish device memory and transfer data between host and device. We've looked at one so far, but there are many, and they may be favored in different situations. We have seen the explicit method where we are using standard C pointers. So we define some pointers for the host and the device. They're defined on the host. We allocate to them, either using the host allocator, malloc in this example, or new if it's using C++ syntax. And then hip malloc to allocate data on the device and provide a pointer to that accessible on the host. And then we copy data between them. Okay, a bit bored of this now, we've done this a few times, but this is kind of the obvious way to do this. The host pointer to the device memory is then used in the kernel invocation because the kernel's all happening on the device, so you need to pass it in the device location in order to do operations. However, these pointers to device memory can't be dereferenced on the host because the host doesn't have access to that memory. And this is perfectly fine, especially if we're trying to transfer large contiguous blocks of data. This is also most likely the fastest mechanism for doing that. That's why we start with it, because while it's a little bit more involved, it gets across the key principles and is usually the best way to go about this. That said, there are other methods for doing memory management and memory transfer. And this particular method can become onerous if there's complex data access patterns or if rapid testing development is required because you have to remember to allocate and move everything every single time. You need to have both references available, you need to set everything up. Okay, so it'd be, in some sense, it might be better if we had a single source for a data object, a single reference to a data object, and then its location is managed by some other system. Okay. And that's where we get onto managed memory. I don't like the term unified memory here because it gets confused with what's happening physically on the device. And people used to refer to this as unified memory, especially in NVIDIA terminology, sort of 5 years ago. And what everyone realized was that it wasn't very performant, and actually they were better off doing the kernel memory. And this unified sense was just the kind of the interface was unified, but actually the memory locations were still distinct. So you didn't really have the granularity of control that maybe you would have liked. So managed memory is allocated on the host with this hip malloc managed. It's in place of the combination of malloc or new and then the hip malloc. Okay, it establishes a single reference to a piece of memory which can be accessed by both the host and the device. The important thing here is you now no longer need to do explicit host device transfers. They are managed automatically as the need arise by the runtime. However, there are performance implications for letting that happen, because what we saw from our little profiling experiment is that memory movement is actually going to be a massive part of the cost of doing operations on the GPU. And if I'm now going to leave that to the device to sort of the runtime, the hit runtime to manage, if it doesn't do that efficiently, then I'm potentially adding a lot of cost into my work. So the schematic usage of this might be I define some pointer on my host. I then call hit malloc manage to generate this a managed pointer for me. Give me a bit of some location in which the data is going to be stored, and then I can use that both on the device and on the host, and it will be transferred as is required. To release the memory, I just need to call my hit free to free the pointer, which is the same as you would do for memory allocated with hit malloc. So what's the mechanism that underpins this? Well, this is called page migration. Transfers are implemented through a process, so this page migration process. A page is a small unit of memory managed. It's often 4,096 bytes on a typical CPU machine. We assume that hit malloc manage establishes memory in the host space, and we can initialize the memory on the host and call a kernel, basically. So I can set up the memory on the host, and then it's going to get moved across when the kernel gets called. When the GPU starts executing the kernel, access to the relevant virtual address, which is the data is not currently present on the GPU yet. It's why he's going, oh, I should be able to access this. Oh, it's not here currently. And the GPU will then issue a page fault to go and retrieve the data and move it across to the GPU. The relevant page of memory then must be migrated and copied from the host to the GPU before useful execution can continue. Likewise, if the data is then required by the host, the CPU, after the kernel is gone, then this will trigger a page fault again, and the memory will be moved back. So Alex here asks, are memory copies with managed memory determined at runtime only, or can it also be managed, happen at compile time? I want to say it's only by the runtime, because you can provide hints, as we'll just come on to, and do prefetching. But it may make optimization choices at compile time, you're correct, but I'm not sure it's going to know which devices it's going to be moving stuff around to necessarily, because you could be calculating where to send the data at any one time. Okay. So we have the ability to do some control with prefetching. So if the programmer knows in advance that the memory is required on the device before the kernel is executed, we can call a prefetch to the destination device. And the schematic for this is say, and at this point, I need to specify the device in which I'm going to. So this is where, when we discussed the sort of architecture of GPU nodes briefly on yesterday morning, about having multiple GPUs per node and the data being moved to them. If you have multiple devices being run and orchestrated by a CPU, then you need to select which one the data is going to be moved to. Otherwise, it's going to prefetch to the wrong location. As the name suggests, here's hipmem prefetch async as an asynchronous call. It will likely return before the data is transferred. Data transfer has actually been moved across to the GPU or back to the CPU. It can be used as a request to the HIP runtime to transfer the data. But for this to work, the memory must be managed by HIP. Okay, this is related to the memory management functionality. So prefetches from the device to the host can also be requested, but you need to provide a HIP CPU device ID. So there's this helper functions which HIP get device, and you can provide either a GPU ID or a CPU ID can be returned. There's documentation on this in the HIP API documentation for more detail. Okay, there's some comments that if you're on Windows, this may not work. This is implemented on Linux currently, but for our purposes, there's not many people here, I imagine, who are using Windows machines for doing this work, but that may be an unfair assessment. Additionally, we can provide hints to the runtime, or what's called advice, basically. You're trying to tell it, well, where should you keep this piece of information most resident? So this is kind of it's less hard than saying you're going to exist on the device in the previous methodology we looked at, where we explicitly do copies and says it has to live in the device. It allows a bit more flexibility, but there's no guarantee that this will be abided by. Okay, you're advising it to do this thing with your data. So there's 4 sort of types here. There's going to be more available, I'm pretty sure, in the documentation, but some standard ones are HIP, mem, advice, set, read mostly. Data will mostly be read and only occasionally written to. HIP, mem, advice, set, preferred location. So you can say, using the device, specified device above, that you prefer a particular location for the data to be held. So if you know or have a feeling from your profile or where you think you're doing the most operations, that the best place for it to be resident is either on the host or the device, or on a particular device, then you can force it to be there. Well, also not force it, you can advise it to be there. And that should hopefully minimize the number of copies that need to occur. If you're only referencing it a couple of times on the host, then you may want to leave it on the device. HIP mem advise set access by data be accessed by a specified device to prevent page faulting as much as possible. So this is again to try to put it in a location which will minimize transfers and using this page faulting method for getting data access. Okay, and then you've got HIP mem advice set coarse grain. Default memory role is fine grain that allows coherent operations between host and device while executing kernels. The coarse grain can be used for data that only needs to be coherent dispatched to boundaries and things like this. So this is a way to get additional performance. Again, you're probably going to get best performance from explicitly locating your data in one or the other. And while this may seem like a simpler mechanism because it removes some of the worries about where your data is located, you may be thinking, why don't we start with this? This is much simpler. I don't have to worry about where things are. It has performance implications. And if you get into, it's not bad habits, but habits of relying on this too much, you may be leaving performance on the table. Okay. Again, all the memory that you're using here must be managed by HIP. Okay, so often you want to start development and testing with managed memory and then move to explicit HIP malloc and HIP memcopy if it's required for performance, and it's simple to do so. So this is sort of, we're talking a little bit about how your workflow might be as you're developing new code. You could start off with saying, I just want to get the framework of my algorithm working, and I don't want to worry about explicitly optimizing memory locations for performance at this stage. I just want to get the flow of the algorithm, the kernels written. I could use managed memory there at that stage to speed me up, and then I could review later once I've had a chance to analyze what's actually happening with my algorithm once I've got my implementation, and then move over to a stricter location-based ordering for memory. Okay, so that's a very quick introduction to managed memory. So we're now going to look at an exercise. It says 15 minutes, but we're going to spend the next half an hour on this, so that there's a chance to do some profiling, and I want people to look at this example doesn't explicitly state this, but I think we'll add this in is to try and use the profiling tools we just had to analyze how RockProf is organizing the data, and where the calls are coming, and see if you can look at performance a little bit as well about how this might differ between using the explicit copies, how the example starts out, and if you start to introduce the managed memory movements around. So if you're keen and get through this very quickly, this will be the last topic we covered before lunch. So feel free, if you get through this and then feel ready to head off, then we'll return back at 1 o'clock. But me and Han will be around till 12 to answer any questions that people might have. Okay, to answer a couple of questions, what are the optimal hints which are interesting to test? I think this is quite simple, so you're probably not going to see a massive performance implication, but stuff like HIP mem advice set preferential location, try to do this instead of having the prefetch, and see if you give it a preferential location, does it sit there? It may be that it takes the first kernel run to sit there and stay there to get the movement to initiate, but play around with it. It's really to get you, with these small toy examples, it's kind of hard to get the full benefit of it because it's really about what's the average thing over the course of a program. So you could do, if you're interested and you have some spare time, is you could just loop over a kernel and set a preferential location and have it do something every nth time to come back to the host and see if you get benefit. And then Sebastian, how does HIP get device work on a multi-GPU runs? And does it work well with MPI, different ranks get a different device? Yeah, so what you do is you usually allocate. So I'm suggesting, sorry, let me finish on saying Sebastian before I jump in there. You would normally, you can do many things about how you divide up your GPU. There are a couple of nice techniques, so where you can subdivide a GPU up, either via MIGing, or there's a way to have different blocks of compute units work together. So you may want to give a separate MPI process to that. But the default is usually to say each GPU gets an individual process, and then therefore they hold one device. And then when you do communication, you can either communicate via just MPI comms, and you have to make sure that you, on your supercomputing center, is bothered to set up the efficient communication between the GPU memories directly, and they do peer-to-peer RDMA transfers. Alternatively, you could have one process per node, maybe with 4 GPU devices, and then you get a number of devices back. I think the way I'd put this is that the device ID is per process, and that's how you can sort of scale up that way. I think hopefully that answers your question. Okay, Pavel. So hints instead of previous. Not necessarily. Hints are doing a different thing, but what I'm trying to say here is that because of the limited sort of scale of the example, what hints are really trying to say is, on average, where do I think my memory should be throughout my program? On average, where do I think my where I'm going to get data access by? And then the runtime will make some decisions based on that. And what it's really going to do is say, well, if I run out of space and I need to access something else, what do I sacrifice? What do I move back to the host for intermediately? And if I'm told a bunch of hints about what should remain on the device, I will try to stick to that advice. But if I can't, I won't. So it's not a strict instruction to store stuff in a location. And prefetch is saying, no, now you need to move it. Please try to move this in advance if you can. But because we've only got small examples, you may not really see a strong effect. But getting used to using them and understanding what they're trying to achieve is important here. Okay, so just before we head to lunch at 12 o'clock, I'll just go through this example very quickly, and then we will break for an hour. And then when we come back, Juan is going to take over for the rest of the course. But if you have any questions remaining, please feel free to email me, and we will get back to you. I'm happy to answer questions, or if people want code snippets to clarify things, please do ask. Okay, so let's just make this a little bit bigger. So in this example, I'm going to do this a couple of different ways. Let me just wrap my example up. So yes, so in this example, we're basically doing the result of the previous one. Okay, this is the common theme through this tutorial. It's meant to try and, as training course even, this is trying to kind of build on things as we go, so you can build one continuous thread of code if you want to. So we're not going to really touch the kernel here. We're more going to change around how memory is managed before and after. And we're kind of asked to do 2 things. We're asked to convert over to managed memory, and then we're asked to look at prefetching. So the first thing we need to think about when we're going to manage memory is that we don't actually need 2 pointers to everything anymore. We only need 1. So we can get rid of all these. We don't need separate device pointers. We can just use the host ones and make them managed, which makes our lives a bit easier and simpler in terms of the way our code is set up. So we can have news of all of these, and then I'm just going to start with, I'm going to get rid of all of this malloc and memcopy, right? We're doing manage now. We don't need this here. We're going to manage it instead. We don't need to set the memory copy kind. We don't need to do the memory copies explicitly. And then we're going to set up our system to run, and then we're going to call our kernel. We're going to peek at some errors to make sure nothing's gone wrong in the kernel execution itself. Remember, this is HIP asserts protecting us on for errors coming from the calls, and then HIP peek error last error is looking at errors inside the kernel itself. And then on the return, we don't need to set memcopy kind again, and we don't need to set back from the device back to the host because we're going to manage it now instead. That's everything. We need to make sure we release our resources. We're going to free everything, but here we're going to switch over slightly. So we don't need to delete. So all I'm going to do is, I will come back to this in a second once I've done what I do to talk about something that confuse you. So I now need to, in the main function, I've removed all my extra pointers to device I don't need, and I've commented out all my existing code here, all my hooks and asserts. So the first thing we're going to say is that in this case, we're going to, instead of doing a memset to begin, hit memset on the device, we're going to kind of prove that this memcopy is really happening by setting, zeroing our array, our output array, to 0 on the host first. Okay, now it's going to run from n from 0 up to n call times n row. And this is going to be h underscore a. I'm just going to set it to 0 at the moment. That's what we did down here with our mem set previously. That means everything has been defined in terms of its values on the host. Okay, and we're not going to do explicit memory copying, but now we are going to do some memory managed settings for these pointers. So for that, we're going to do a new section below. And actually, to speed us up, because we're going to, it's almost lunch and everyone probably wants a break. I'm just going to start copying this to make this work out. Alloc and this thing. Okay, hit my manage. So now these, oh, I need to do the other thing, which I will forget. Make a problem if I don't. These need to be the host pointers now, not the device ones. Okay, so I've deleted the device pointers. I've not allocated them. I've not copied the data from the hosted device. I've just set the data in the host pointer, and then I've told HIP to manage that particular pointer. Okay, I'm then going to do everything I've done before, call my kernel, check for errors, and the last thing I need to change down here at the bottom is I no longer need to delete these device pointers, sorry, these host pointers, because I've got them managed. And instead, I'm going to free them with hip free. Okay, and that should be everything. I did compile it earlier, didn't I? Yes, right. Of course, I've got wrong. Yeah, so now I've done the other obvious mistake, which was not to remember what I'm passing into my kernel. So now I need to remember that my kernel is not getting past, is not going to use device versions, it's the host versions, because it's now managed by him. By compiling again. We've got the same submit script as before. A bit bigger. Okay, that's run. That is correct. Yes, I've got the correct results. And then I can just cat out the results .stats.csv. Okay, and I do get something that's not reasonably performant. It's not as performant as we saw before. Oh, okay. I'm getting internet fixed here. I will make sure this code is shared. Okay. Apologies if this is my end that's causing the intermittency. Well, I've created new versions of these, and they're on the host. And then I'm just saying, go manage them. I'm just saying manage it. I'm not saying need to remalloc it. I'm just saying you're going to manage this data size. Okay. So I can then move on to prefetching. Have I just done a stupid thing? I may have done a stupid thing. I need to read the documentation whether hip malloc managed is actually mallocing the space or whether it's just managing an existing object. I will come back to you. It may well have been a double malloc, but then that is great. The solution is kind of obvious. I just don't need to create a new, and then I need to make a new malloc, and then I need to assign the values on the host side. Okay, sorry. Then I've made a mistake here. So maybe I'm using undefined behavior. That was my bad. double checking my setup a minute ago. But I think you guys get the principle here. Yeah, but if I don't do the first malloc one, then I do need to change the ordering of this operation. But the point I'm trying to demonstrate is that you can do the malloc. So you can set malloc manage, then you set the values on the host side, and then the management's happening all on the device. And then when the kernel is called, it's pulling data over as you require. I can also then add in the prefetch, which I'll just do quickly. So before my kernel, I want to make sure some of this data is moved over. I can have prefetching of all three of these items. Okay, and then that can get copied across in advance. Device num is set above via, there's a call to hip get device count. No, that's not device count here, sorry, hip get device. Something that does device number somewhere. Yeah, sorry, hip get device gives you device number to be run. Okay, and I can then run that and I get some performance out. That is faster, and I will give you some results. So I've got here a Profetto output of these. If I just bring it up. So again, if I open a trace file, I've got two examples. So if I just open the fast one to begin with, give it a second because it's being a pain. I can then do what I did before, and I can inspect where I'm getting. Can I see that my prefetches are happening? Yes. Memory prefetch async 1, 2, 3. They're all happening before the kernel call goes in. If I just expand this, sorry, kernel launch is there. Then a bit later on, I've got a tiny kernel call down here. Okay. Now, if I look at slightly different results, and what I've done in this slightly different case is to comment out one of these prefetches. I've taken the biggest one, and I've not done that as a prefetch, okay? And that's what I'm going to do in the next example file. And I've measured that. So whereas before I had 3 prefetches, now I have, if I get to the right location, I only have 2, okay? But the size of my kernel has become much bigger because of that. Because now I'm having to wait to make sure the memory is in the right location during my kernel execution. Whereas before I had a much smaller kernel copy because I've already done the prefetching. So it's like 15,000 nanoseconds. This is 300 something. So it's an order of magnitude worse, at least. Okay, so hopefully that was instructive. It's now time for lunch. If you have any questions about this and any other clearly and obvious mistakes I've made in my programming as I'm demonstrating this, but the point here is the managed memory gets you access to the data without having to explicitly tell it where it needs to be at times. And doing prefetching does help. It gets added as a separate area, so the time is counted differently. So if you go to prefetch, there's a separate prefetching called here. Okay, so memory set prefetch asynchronous is running 100 milliseconds and then 100 microseconds, and then my kernel is getting called. What I was hoping to see, and you will see in the NVIDIA tools, is you will see an explicit tick for a page fault if you haven't prefetched. If it gets to the kernel and goes, oh, I need some data, it logs the fact that it's had to go out and do a page error, and that can be very useful. It's a series of blue and red ticks along the bottom, so you can very clearly indicate when you're page faulting and where there may be opportunities to optimize by doing extra prefetching. Yeah. So when we come back from the break, when we come back from lunch at 1, why not take over and we'll start talking about shared memory. And this is memory when you need to start thinking about trying to accumulate things within compute units and warps, and then move on to things like constant memory and more importantly, streams. This is how you can start to improve packing. The kernel times are different between the two. If I don't prefetch, then I have a significantly longer duration. But if I do my launch times 4 milliseconds, my launch time here is something like 10 milliseconds. But I suppose I'm in this case, I'm doing everything to it. So I think it's being taken up by inside the kernel itself. That's what you normally see in NVIDIA tools, but you'd have a much clearer signal that there is a page fault happening in the kernel. Okay, we'll stop this session here, and we will return at 1 o'clock after lunch for the next session. Okay, so Lorenzo's question, if you prefetch after the kernel, you're going to tell it needs then, before the memory gets touched again, so that the place that the memory gets touched again, I believe, is when it does its test. Yeah, so it's going to touch h_a and h_x_y to test the answer. It's going to try and the prefetch on return is going to try and copy it back to the CPU side, the host side, before it does that operation. So hi Sarah, I can try to set the code. Matthias, if the following is correct, because we have managed memory, the prefetch, we have page faults during the kernel, which causes the runtime to increase compared to the version without managed memory and with explicit company. Yeah, so if we just use managed memory, when the kernel executes, it's going to go, it doesn't have the pointer's not currently, the managed pointer is not currently on the device, the memory you want is not there, it's going to cause a page fault, that's going to take a delay, it's going to go and get that data from the host, transfer it over, and then operate on it in the kernel. The prefetch says, try to avoid this page fault, because I know I'm going to need this. So I'm telling you in advance runtime, you're going to need to copy this. So don't wait till you get to the kernel to do it. Do it in advance, please. And it may be able to do that in advance, or it may end up just getting to the kernel and go, oh, now I need to do it. Okay, you don't have firm control over that. It's something that can happen asynchronously while the work's happening, which allows it to hopefully copy in advance of the execution. This can reduce the number of page faults that the kernel might have to execute, cycles go through. The reason you're getting you're still getting a performance degradation compared to the other copying version, because guarantee that the kernel has all the information in advance. You're implying it should do, but you're not explicitly telling it must wait, barrier, do a thing, and then complete before moving on to the kernel operation. So it's just allowing you the opportunity to be asynchronous in the way you move data around, but it doesn't. But because you're allowing the runtime to make decisions, you have a much higher chance of giving a performance penalty. Thanks, everyone. Have a good lunch, and one will begin again at 1 o'clock.